Right. So second, I've rewritten and open sourced the advanced piece of software on which my research over the past decade has been based. This code is capable of modeling magnetized compact objects such as neutron stars and white dwarfs, as well as magnetized fluid flows in dynamic spacetimes that are inhabited by black holes, white dwarfs, and neutron stars. This code must be coupled to another that evolves that solves for the metric in Einstein's equations in GR, general relativity, so that the full combined code is capable of generating theoretical predictions, not only of gravitational waves, but also giving us some idea of what sort of electromagnetic counterparts we might observe to these, for example, compact binary mergers as a result of GR-MHD phenomena. Now, as you might imagine, the equations solved by the combined codes are highly complex, and the computational fluid dynamics algorithms themselves are rather complex as well. And in fact, the original code on which Illinois GR-MHD is based took about 3 years for a new user to master. And this new code I've just released, Illinois GR-MHD, is designed to minimize this learning curve. So let's turn our focus now on new techniques for compact binary merger simulations. This work is a result of a collaboration between the University of Illinois, NASA Goddard, and West Virginia University. Oh, and here's my paper's phone number in case you feel lonely tonight. Give it a call. So what's our motivation for doing this work? Well, as two compact objects like black holes or neutron stars orbit one another, their orbit shrinks as gravitational waves sap their orbital energy and angular momentum. LIGO consists of a pair of ultra-sensitive interferometers. There's one here in Washington, which I can't wait to visit this weekend, and another in Louisiana, designed to detect these very faint gravitational wave signals as they impact the detector. In so doing, LIGO will open a new window on the universe, potentially teaching us volumes about the nature of neutron star matter and the populations of compact objects, binaries in the universe. So here I show a signal of what might be observed by a gravitational wave interferometer like LIGO. So we see a wave. But what we can learn about the universe from such an observation will be limited by how well we can map this information into information about the sources generating it. So the bottom line is, when a gravitational wave is observed, we need to answer the question, what produced this? Considering different neutron star equations of state, black hole masses, spins, etc., we know the parameter space of possible answers is large. And filling the space with a corresponding set of theoretical gravitational waveforms through merger, when the gravitational wave is generally strongest, will require a large number of computationally expensive numerical relativity simulations. And as most of us know, the task of making these observatories sensitive to gravitational waves is monumental. But theorists face the daunting task of producing a library that maps gravitational wave observations to the exact systems that produce them. Such a library is far from complete, and building the library will be very computationally expensive. The computational challenge spawns from the fact that generating theoretical predictions from gravitational waves requires, at a bare minimum, solving Einstein's equations of general relativity, which comprise, of course, his theory of gravity. The equations of GR, as we know, are very complex, they're nonlinear, and solving them for many systems of astronomical interest requires a huge amount of computing power, typically on supercomputers. But at the heart of the computational challenge lies an arguably even greater one, which seeks to find an optimal formulation of Einstein's equations for solving them on the computer. Figuring out how to formulate Einstein's general relativistic equations in such a way that makes it possible to solve them on computers is a long-standing problem in numerical relativity. Just to give you an idea, one of the simplest problems in Newton's theory of gravity, namely that of solving for the gravitational field of two point masses orbiting one another, is quite simple. One can generally solve this on the back of an envelope in a few minutes. The same problem in Einsteinian gravity, namely that of two orbiting black holes, took nearly 100 years and a focused, multiple decade search for a formulation of general relativity stable in the presence of orbiting black holes. Then in 2005, three groups of numerical relativists succeeded in solving this problem, devising two completely different formulations of general relativity. And these approaches have been used in nearly all numerical relativity simulations since. Now, I can't stress enough how important these formulations have been at bringing numerical relativity into this new age of gravitational wave astronomy. So my message today is simple. Although these formulations of general relativity are incredibly robust, in the decades since they were first introduced, we've discovered that they're far from perfect. Today I'll describe the most widely used formulation, called the moving puncture approach, and describe how we modified this formulation to significantly reduce errors in our calculations. Though I'll discuss our improvements in the extremely challenging context of two orbiting black holes, this widely adopted moving puncture approach has been used in a majority of other numerical relativity simulations since it was first devised, including those of binary neutron stars and black hole neutron stars. So the improvements I present today have the potential to lead to improvements in numerical relativity simulations adopting this formulation across the board, including applications outside of LIGO, for example, to electromagnetic counterparts of gravitational wave signals that are observable by traditional telescopes, like the Green Bank telescope, of course. In other words, improving this widely adopted formulation of Einstein's equations has a potential to immediately improve most numerical relativity simulations, which themselves may be critically important for advancing our theoretical understanding of current and future astronomical observations, and by extension, the universe at large. So as an introduction to our new techniques, let's first review how we solve Einstein's equations of general relativity in a numerical relativity context. I think it's best explained through illustration. So general relativity, of course, describes a four-dimensional manifold corresponding to a curved space-time that describes the gravitational fields around massive objects at all times. Now, for the purposes of numerical relativity, for example, Einstein's equations of general relativity are rewritten as an initial value problem, consisting of a set of time evolution equations and constraint equations, just like Maxwell's equations of electrodynamics. Now, in most numerical relativity formulations of Einstein's equations, we need only to specify data on the initial three-dimensional spatial hypersurface at time t equals 0. Then to construct the next spatial hypersurface, we simply evaluate the time evolution equations, and we repeat this cycle as we build the space-time one hypersurface at a time. Now, the time evolution equations can be split into two categories. First, gravitational field evolution equations, which describe which govern the physical description of the space-time. And second, coupled to this, are the set of coordinate gauge equations, evolution equations, which describe the coordinate dynamics in our four-dimensional manifold. And here's how we specify coordinates. We introduce four variables: a three-vector called the shift, beta, and a scalar, alpha, or the lapse. So this picture shows how a three-dimensional coordinate, xi, evolves from one spatial hypersurface to the next. So from t hypersurface to t plus dt hypersurface. So the lapse specifies how far the xi propagates along the unit normal to the t hypersurface. And the shift shows how, the shift measures how far it moves within the next hypersurface. Together, they give the precise space-time point, a location of the coordinate point at the next spatial hypersurface. Let's take a closer look at this 3+1 decomposition of Einstein's equations. As a reminder, the standard hyperbolic PDE is the wave equation, which describes the propagation of a wave through space and time. In fact, the time evolution equation for the lapse in the moving puncture formulation takes this basic form in a principal part analysis. Now here's the actual principal part equation governing the dynamics of the lapse. Notice the wave speed is v, in this case, is the square root of 2 times alpha. Alpha is a quantity that goes from nearly 0 in the strong field region around the black holes very quickly to a number approaching 1 as you get away from the strong field region. Now in the physical units of our equations, the speed of light, c, is 1. So lapse waves, given that alpha is very close to 1 away from the black holes or strong field region, lapse waves propagate at about the square root of 2 times the speed of light. Now this kind of makes sense intuitively, as we would hope that our coordinates would settle faster than the fastest physical waves in our simulations. In fact, here's what it looks like for a lapse wave propagating away from a binary black hole in one of our calculations. So this is a plot of lapse versus distance from the origin, where the black holes are initially orbiting at a distance of 5 in these units. Notice the lapse is plotted on a nonlinear scale, and that it approaches 1 very rapidly as we move away from the strong field region near the black holes. Now from the start of the calculation, in black, the lapse quickly equilibrates near the black holes. You can see that sort of in the blue line. And a lapse wave propagates outward. That's this blue guy right here, propagating outward. And red is a settled lapse. So this shows you the transition between initial and settled. Notice that at time 103 m, the lapse wave has propagated out to about a distance of 140, again corresponding to this wave speed of approximately the square root of 2 times the speed of light, just like we anticipated. Now the lapse propagates at the fastest wave speed in our system of equations, and we found that by tuning its behavior alone, the equation governing the dynamics of the lapse, we found that we've been able to reduce errors in our simulations by more than an order of magnitude. But before we can understand the nature of the problems with the moving puncture formulation of general relativity, we must first understand how errors come about in our simulations in the first place and how we measure them. So recall that our decomposition splits Einstein's equations into a set of constraint and time evolution equations. The main source of error in our simulations comes from evaluating the derivatives within the time evolution equations. And if our errors are 0 in these equations, then our constraint equations will remain satisfied to the level at which we started with our initial data. Now, although our errors are never 0, they are in principle well understood. We solve our equations on a numerical grid, shown here by these blue dots, represented by those blue dots, and we use a finite difference approach to evaluate derivatives on this grid. The technique's pretty straightforward. We simply analyze a Taylor expansion around a given point on our grid x0, shown here as a red dot. Now we rearrange the terms in this expression so that f prime of x0 is on the left-hand side as follows. So f prime of x0 is equal to, well, this is familiar. In the limit delta x goes to 0, this is an exact expression, right? This is the definition of derivative. So what we do is we call this the error term. And for this representation of derivative, we call, since the error term goes like the grid spacing delta x to the first power, we call this a first order representation of a derivative. So in the limit delta x goes to 0, the rightmost terms have to go to 0, and we call these, of course, the error terms. And you can imagine we could keep more terms in this Taylor expansion to get a higher order derivative operator. In fact, we use 6th order accurate representations for spatial derivatives and 4th order for time. So when we perform these calculations of orbiting black holes to get theoretical predictions of gravitational waves, we expect our errors to drop as the 4th to the 6th power of the grid spacing in space and time. So as we increase resolution, the numerical solution will quickly approach the exact solution. At least that's how it should work in principle. In reality, making errors small and manageable in these calculations when the level of accuracy required increases is not an easy task. To understand this, consider the numerical grid we need in order to solve these equations for a pair of orbiting black holes. So let's start by imagining this blue cube here as our three-dimensional numerical grid with grid spacing delta x. Because black holes curve space-time very strongly, the grid spacing is going to have to be much smaller than the length scale of the black hole horizon, set by the black hole horizon. Further, there exists no exact outer boundary conditions for orbiting compact objects. So error from our approximate boundary conditions will propagate inward and could poison our calculation. So how do we solve this problem? Well, generally, we push the outer boundary so far from the black holes or the compact binary that they're out of causal contact from the black holes or the compact objects. What I mean is they're so far away that no wave has time to propagate from the outer boundary and into the region of physical interest in our calculations. This high-resolution grid extending to an enormous outer boundary is computationally impractical, as it would require about 10 million gigabytes of memory just to store all the grid points for a typical orbiting binary black hole calculation. This is more memory than the top 500 supercomputers in the world combined. Finally, remember that one of the main goals of this calculation is to produce theoretical predictions of gravitational waves from this system. Now, close to the black holes, the gravitational waves interact nonlinearly with each other and don't represent what we would observe when we look for gravitational waves here on Earth. So somewhere between the black holes and the outer boundary, we must measure gravitational waves. And thankfully, the resolution requirements for modeling gravitational waves is much lower than the requirements near the black holes. So our solution is to perform these calculations on non-uniform numerical grids, with highest resolution grids at the black holes and progressively lower resolution grids as you move out. In total, we drop the resolution 11 times in our, typically around 11 times in these compact binary evolutions. And the outer boundary box size is about 4,000 times larger than the black hole box size. This technique, of course, is called AMR, or adaptive mesh refinement. And in principle, it solves all the problems I just described, and thus has been used in most numerical relativity calculations. This figure gives you an idea of what the three-dimensional grids look like. Near the black holes, the grid spacing is delta x, and this box is embedded in a larger box with grid spacing 2 delta x, etc. In this way, the number of grid points at each resolution remains more or less constant, and we put most resolution where we need it, at the black holes, in this case. Although AMR has been a real godsend to numerical relativity, making it computationally feasible to perform large numbers of these orbiting compact object calculations with minimal computational expense, my colleagues and I believe it may also be responsible for many well-known but poorly understood problems observed in numerical relativity calculations. So what sort of problems do I speak of? During binary black hole calculations, for example, as we construct the space-time one three-dimensional hypersurface at a time, we monitor the L2 norm of the violations of the constraint equations versus time. These violations correspond, as I said before, to numerical error. Here's a log-log plot of the L2 norm of the Hamiltonian constraint violation versus time in one binary black hole calculation. Because we expect between 4th and 6th order convergence from our finite differencing techniques, this curve should drop by a factor of between 16 and 64 if we double our resolution. Instead, what we see is a drop of around 3 to 4. In fact, as we'll soon see, this poor convergence is also observed in the gravitational waveforms from binary black hole calculations. So one quantity of key interest in our simulations, the gravitational waves, is not converging like it should when high accuracies are called for. This is a serious problem because it means that we do not have a firm grasp on our errors. In summary, although the moving puncture AMR paradigm is extremely robust and is the most widely adopted technique in numerical relativity for performing compact binary merger calculations and simulations, when it's pushed to very high accuracies, gravitational wave convergence issues are observed. This is bad. Or as Darth Vader would say. Now, it's been hypothesized by others that these gravitational wave convergence issues may be related to errors from AMR boundaries. These errors are most obvious at the beginning of binary black hole waveforms, as shown here. So this waveform is a repeat of an industry standard so-called NRAR binary black hole run, in which one black hole has a spin parameter of 0.3 aligned with the orbital angular momentum, and the other black hole is non-spinning, equal mass. All the results I present in this part of my talk are in the context of this physical scenario. And when we do a Fourier analysis of the Inspiral waveform, we see two strong spikes, one corresponding to the physical gravitational wave, which you can see has a wave period of about 100 m, and another corresponding to the noise with wave period of about 10 m. Now let's take a look at this power spectrum, zooming in on the noise. Notice a spike at the dominant noise wave period of about 10 m. Again, there's another spike corresponding to the physical gravitational wave, but that's at a period of about 100 m, way off to the side of this plot. Not shown. So this is from our low resolution run. What happens when we increase the resolution? Notice that regardless of the resolution chosen, the noise spike is unaffected, retaining its strong amplitude. In other words, the noise does not go away with increasing resolution. We found a non-convergent error, in other words.
Yes? How do you know you're not picking up here just the giant radiation?
Oh, because I did the FFT myself, and I chopped off this part effectively. So there's a window here, yes. Smooth. It's like a Gaussian window, and it's 0 practically in this region right here, and it goes to about right here.
So you remove the first 100 m. Is that what you said?
Yeah, about that. That's about right. Yes. So the idea that gravitational wave convergence issues are due to this stochastic, numerically driven noise is certainly plausible. But how might we reduce this waveform noise? Well, as I mentioned before, one clue came from some of our colleagues. It's probably from AMR refinement boundaries. Here again is a schematic of our AMR grid and what it looks like, focusing highest resolution in the strong fields around the black holes and lower resolution away from the strong field region. Now in these calculations, the number of waves propagate out from the binary. They can be gauge waves, that is, waves that correspond to the dynamics of the coordinates in our calculations, physical waves like gravitational waves, and constraint violating modes from numerical errors. Now consider one of these waves propagating from the binary. Now as the wave propagates outward, the AMR refinement boundaries are going to act like a poor high-pass filter, so that waves with high-frequency components will partially reflect from the boundary, generating noise, and the part of the wave that's transmitted beyond this coarse level will still have high-frequency components that will be poorly resolved, and poorly resolved waves will lead to large numerical errors. And given the nonlinear nature of the equations we're solving, big numerical errors in one quantity can spread to errors in all quantities, including, so in other words, errors from gauge wave propagation can translate to errors in gravitational wave and also constraint violations. So as I said, one clue to what's causing this waveform noise is that it's probably from AMR grid refinement boundaries. Baker et al. Provide perhaps some further insight, finding that the initial outgoing lapse wave early in binary black hole evolutions possesses sharp, high-frequency features, driving spikes in the Hamiltonian constraint violations as the lapse wave smashes through progressively lower and lower resolution refinement boundaries and is under-resolved. Now, we know that the Hamiltonian constraint violations exhibit poor convergence, just like our gravitational waves. So we must ask if this initial sharp outgoing lapse wave may be causing our waveform convergence issues as well. Regarding Hamiltonian constraint violations, here's what I'm talking about. So this is a log-log plot of the L2 norm of Hamiltonian constraint violation outside the horizons versus time. The blue vertical lines denote the refinement boundary crossing times for an outgoing initial wave propagating at a speed √2 times the speed of light. Notice each time the wave impacts a refinement boundary, it generates a great deal of Hamiltonian constraint violations. We strongly suspect that this is caused by the lapse, as the principal part analysis of the equations we solve indicate that the lapse actually propagates at this speed, √2 times the speed of light. So our working hypothesis is that constraint violations and waveform noise are both due to the bulk of the constraint violations and waveform noise are due to the sharp initial outgoing lapse wave impacting AMR refinement boundaries. Yes?
Zach, are you going to tell us what condition you're applying at the AMR boundaries? I mean, because different groups are doing different things, right?
Yes, it's true. So we're doing what's standard in the carpet infrastructure, which is Lagrangian interpolation. So just fit it with a polynomial and interpolate accordingly.
Is it first order or?
No, it's fifth order.
Fifth order in time?
So it's, well, in space. Second order in time, but we have very small time steps here. And we've tamped down those time errors to where they're not dominant, as you'll see. Yeah. Did you have a question?
Yes. When you showed what happens when you change convergence, right? Essentially, your errors at all except one particular period or frequency were going down, and they were sort of staying fixed at one particular frequency. So clearly,
well, that wasn't it wasn't a measure of error that I was showing. It was just a demonstration that the noise itself. So this is noise, and you would hope that we know that this is noise. There's no physicality to this stuff here. So we were hoping that maybe it would diminish with increasing resolution, but it doesn't.
Right, but I guess so my question was, there must be something special about this particular period, right?
Yeah. So rewinding.
But not at 10. So I'm wondering.
Yeah. So rewinding a little bit, you'll see actually this outgoing lapse wave. Wow, a lot of slides. Too many slides. Okay. This outgoing lapse wave, if you look at this, it has a period of order, or a wave of wavelength of order 10, roughly, and I think that's what sets that scale.
And is that because of the size of the initial size of your grid, or I mean, what sets this period?
It's a good question. So.
Isn't it the separation? Isn't this the typical scale of the separation?
Actually, that is true. That is a very good point, and that does kind of make sense actually. Yeah. So the black hole separation initially is 10 here, believe it or not. Yeah, that's very insightful. Good.
But if you change your AMR grid structure, does
Yes.
that change then?
Yeah, it does. It does a little bit. Well, no, not this. No. Not this. I mean, so what happens is as this impacts refinement boundaries, it becomes progressively, it changes, of course.
It changes shape.
Just because of error, right?
Right, but you can test whether this is the initial separation and not the AMR hierarchy by just changing the hierarchy. Just saying.
Yes, you can certainly adjust that if you like.
The AMR doesn't have that scale. You have boxes that can be 100.
But they're going to tend to have the scale of the separation, right? Unless you do something else.
It can't be orbital separation, right? That determines the orbital period. And your radiation is the junk radiation, not junk. Whatever you're seeing, that spike, is at a much higher frequency, 10 times higher frequency.
It's the noise spike is at a period of 10 m, and that's the exact same as the orbital separation.
That means that
the orbital period in this case is about 200, and so the gravitational wave period is about 100 m, and that's what you're seeing here. This is physical, but of course this zoom in here. This is the noise with the period corresponding to about the orbital separation. Assuming speed of light equals 1, which it does, approximately. Great. Great. Right. So we think that the lapse is responsible for the outgoing lapse wave, given that its propagation speed and the timing of these bumps in our Hamiltonian constraint violation, L2 norm versus time. We were fairly confident that the lapse is behind this. So we focus our efforts on modifying the lapse equation. Notice again that taking the principal part of the lapse yields a wave equation with speed √2 times alpha. And again, since alpha is very close to 1, just outside the strong field region, this means that it propagates at roughly the square root of 2 times the speed of light. Our first modification of this lapse equation replaces this speed factor of 2 with a function g of r, which increases from 2 monotonically in the strong field region to a number much larger. I guess this is the root of that. So g increases to about 100 going out to the outer boundary. Now in this way, by accelerating the lapse wave as it propagates outward, the front of the lapse wave will be propagating at a slightly faster speed than the back of the lapse wave. And the net effect being you stretch it out. You increase that wavelength so that it can impact more AMR refinement boundaries before its numerical errors really spike. So we would anticipate that by stretching out this lapse wave, we should reduce our Hamiltonian constraint violations. And that's exactly what we see. So this is the fiducial control case, the OldGauge, and this is with this stretching enabled. Notice that brown's before the improvement and green is after stretching. But notice that there's a stubborn initial spike here, and it's unaffected. We believe its existence may have something to do with the initial settling of the gauge. So our second modification focuses on speeding up the evolution of the gauge dynamics with respect to the rest of the PDEs, forcing the gauge to settle faster. Now we accomplish this by multiplying the BSSN right-hand sides, that is the right-hand sides of our gravitational field equations, evolution equations, not the gauge, by some function f of t, which is less than, which starts out very small and increases very smoothly and slowly to 1. So once it reaches 1, we just have the standard BSSN right-hand sides. Now we actually showed in our paper that this trick is exactly equivalent to another change in the gauge. So we're still allowed to do this by virtue of gauge freedom. But does this trick kill the initial Hamiltonian constraint spike? The answer is yes, it does. That's shown here in purple. So our third and fourth modifications focus on smoothing and dissipating high-frequency features. Yes, please.
So can you go back to the... I would have expected the magenta line to just have a peak at the same time with reduced amplitude, while the peak is just shifted in time. Well, it's reduced. It's
reduced and it's shifted in time, and that's partly because the lapse wave is actually is propagating at about... effectively, it's propagating at something like 30 times the speed of light.
But that's what the green
initially.
Does. The green speeds up the lapse.
Well, okay, so both actually. So what I'm talking about is with respect to the BSSN evolution, the lapse is actually accelerated significantly. So it propagates out a lot farther by the time, it's able to propagate out much farther than previously. So think of it like this: we press fast forward on the lapse evolution early on, and also the shift actually early on. But the BSSN fields, the actual physical gravitational fields, are evolving very, very slowly with respect to that. So the lapse is pushing it out, is being pushed out much. And so this corresponds to the physical time, right? So this corresponds to the BSSN effectively, what the BSSN variables, how they're evolving.
Just let me tell you, or tell me why is it that I'm thinking in the wrong manner. You said most of these problems come from the fact you have a gauge wave which is imprinting the refinement boundary, and this is producing reflection and all of this mess. Your solution to this problem is speed up the speed Well, if you say that
So the green is the acceleration, yes. That accelerates it
but then I would
significantly.
expect that the first peak happens earlier because I am impinging the refinement level at an earlier time because I'm making the gauge wave.
Oh, move faster, yes.
So why is it that instead?
I don't think this, in other words, I don't think this has anything to do with an AMR refinement boundary necessarily. I think this spike, in other words, has something to do with the fact that the gauge it can't settle fast enough with respect to the gravitational waves and reach an equilibrium fast
The
enough.
first spike is not reflected.
I don't think so. I don't think it has anything to do with AMR. And I mean, you can see this is it would have to be very, very close in. And I think we have very good resolutions that close in. Right, so we're starting at the binary, and at a distance 10 away from the binary, we still have pretty good resolutions, and I don't think we're getting large errors there. Yeah. So our fourth, sorry.
Is that the later part actually real, meaning it actually goes to zero towards much later time?
Oh, this down here? Yeah.
Is
Well, no,
I mean-
it remains constant. This is the property of BSSN. We don't. Violations of the constraints are not dissipated, are not done. I mean.
So what you think we're just diluting it somehow, and that's why
No, I
it's
think it will just level up. It will not go to zero.
well, fine, not go to zero. Yeah.
Well,
it won't drop off either.
I mean, it'll never go to zero. I'm not going to argue that, but I'm not sure if we continue this evolution for 10,000 more m that it would not be. It would plateau.
well
I don't
we
know.
actually have done this because you know, we've tried a different approach to solve the same problem, which is not using, which is to use different formulations of the equations, not only us but also other people,
Sure.
which actually introduce damping terms.
Right, the
And
Z4C
what we do
and
is
so
we
forth.
can
Yeah.
see that the SSN levels off because the affection speed of the constraints is zero,
Mhm.
while if you introduce damping, then you have an exponential damping of that.
Right. So our third and fourth modifications focus on smoothing and dissipating high-frequency features in the lapse. In particular, the third modification adds a parabolic term to the right-hand side of the lapse. And the fourth modification adds much stronger Kreis-Oligher dissipation to the lapse than is typically used. The net effect is another significant reduction in Hamiltonian constraint violations. And for our final modification, we reanalyze this G of R acceleration term, and we find a term that actually accelerates the lapse even more and has a net effect, of course, of stretching the lapse wave even more, even further. And that has a net effect of another nice reduction in constraint violations. And notice that the BestGauge case reduces the Hamiltonian constraint violations on average by about a factor of 20 compared to the standard gauge choice. But does this reduction in Hamiltonian constraint violations translate to a reduction in waveform noise and perhaps an improvement in waveform convergence and with increasing numerical resolution?
Zach,
Yes.
This statement of 20
That's a time average.
Like, but is this also true at any resolution?
Actually, that's a very good point.
Because these are rather low resolution, right?
Yeah, they are. They are. Let me think about this. Yes, actually, it does get much bigger with increasing resolution because with increasing resolution, you get better convergence. It turns out with Hamiltonian constraint violations with these better gauge conditions. So there are two effects. One is the lapse wave is producing less numerical errors, and second, that you're getting better convergence in the L2 norm of the Hamiltonian constraint violations. So actually, in the paper, we said, I believe it was a factor of 60 at the very high resolution, OldGauge versus our BestGauge condition.
Okay.
So it gets better with increasing resolution. So recall that with the standard moving puncture gauge conditions, we observed a spike in the Inspiral gravitational wave power spectrum that was not affected when we increased resolution. We suspect this noise-generated spike may be behind our waveform convergence issues. But so what happens to this spike when we adopt our best gauge choice? So I show here the very high resolution OldGauge run here in black. This is the power spectrum for the OldGauge, compared to the best gauge that we found. Notice that this spike that corresponds to the noise has been completely eradicated. And what's left appears to be, what little spike is left appears to be converging away with increasing resolution. So do we see better convergence now in our gravitational waves? Here's a waveform phase and amplitude convergence order versus time throughout much of the Inspiral. We expect about fifth order convergence in these evolutions, corresponding to the spatial interpolation order at AMR refinement boundaries. And as you can see, the actual convergence order with the old gauge fluctuates significantly from that. Now, I should point out that the weird convergence or behavior at merger is expected as the black holes merge at slightly different times depending on resolution. So effectively what you get is a big change in phase, and amplitude drops very, very far, orders of magnitude immediately. But the oscillations elsewhere in convergence order are simply unacceptable. So what happens in our best gauge choice? Well, I'm going to flip back and forth to show you. So here's old gauge, best gauge, old, best, old, new. Notice that the waveform amplitude and phase convergence are spot on fifth order. So it seems we've fixed the poor convergence properties observed in the old gauge choice. Now that we have a trustworthy convergence order, we can reliably Richardson extrapolate our results using only 2 resolutions of data to generate Richardson extrapolation-based error estimates. So here we generate 2 realizations of a Richardson extrapolated waveform amplitude. The first Richardson extrapolated waveform uses data from the 2 highest resolutions for a given gauge choice, say high resolution and extra high resolution, assuming fifth order convergence. And the second Richardson extrapolated waveform uses data from high resolution and medium resolution. So the difference between these Richardson extrapolated realizations of waveform amplitude corresponds exactly to a numerical error. So in other words, the difference will give you an error estimate. And in this way, we find that the normalized amplitude errors in the old gauge are about 40 to 50% higher than with the best gauge. Similarly, the phase error in the best gauge choice drops by about 40%, old versus new. So, with negligible increase in computational expense, we've managed to reduce Hamiltonian constraint violations by more than an order of magnitude. We've removed the noise spike in the gravitational wave power spectrum, yielding far cleaner convergence in gravitational amplitude and phase. And we've reduced our in-spiral phase and amplitude errors by about 40%. Whew. There's a lot of work. So in the future, but it's not finished. In the future, we like to try other binary black hole scenarios, different mass ratios, different spins, high order finite difference techniques to see just how far we can drop our errors now that our noise is at such a low level in these evolutions now. And by no means do I mean to claim that our gauge condition is perfect or optimal. I imagine there is plenty of room for improvement. And finally, there's a promising statement that I've made previously, and I'll make it again. We'd like to try these new gauge conditions with other compact binary merger scenarios, including those with matter like black hole neutron star or binary neutron star, and see just what sort of effect that may have on the waveform. It may be that we don't see any effect. It may be that we'll only see an effect with very, very high accuracies that we've not yet attained. So any questions on that part of the talk? Oh, sure. Please.
In the first line of your improvements, but you said with negligible increase in computational expenses. But what CFL factor do you use?
0.25.
So can you increase CFL factor by, for example, to 0.4 or 5 with your G over conditions?
No, and the reason is we want the dominant. So there are different convergence orders that are competing in this calculation. There's the there's a spatial prolongation error, which is fifth order, and that seems to be dominant, as you saw. There's time. There's the time finite differencing errors, which is fourth order. We use RK4. There's a spatial differencing error, which is sixth order. But then there's the time interpolation error at AMR boundaries, and that's second order. That really does restrict us to dropping our CFL factor, and I don't anticipate we'll be able to fight that too much, although I didn't really try, I have to admit, with the best gauge choice. I didn't try a higher CFL. If you can do that and you still get these nice improvements, wow, that would give you a factor of 2 improvement in your performance immediately, right? That'd be great. Okay.
I'm asking a question. I have a question about your choice of G over function G over.
Yes.
I think your choice of G over from your preference seems to contain some magic numbers. I mean, some numbers are chosen adapted to your AMR structure.
Yeah, it has to be according to your AMR structure. Otherwise, because you're competing against the CFL condition, right? I mean, you can't propagate waves infinitely fast in these explicit hyperbolic schemes. So, yeah, that's one of our restrictions. So we did, I think I mentioned in the paper that we tried another realization of G of R that actually allowed a much steeper acceleration. And that dropped Hamiltonian constraint violations significantly from what I even showed in the best gauge case. But unfortunately, that lapse wave hit the outer boundary so fast that it created an enormous reflection wave. And so what we would see in our amplitude, gravitational wave amplitude versus time, was this nice smooth thing and then suddenly a wiggle corresponding to that lapse wave that hit the outer boundary coming back. You don't want that. So what we found is that this sort of it might be a sweet spot, I don't know. But you're right, there's some magic that has to be, I won't say magic, I'll say there are considerations that must be, that must be accounted for, corresponding to your local CFL factors on your grids and the exact grid structure that you use.
Okay, I had a question also related to CFL.
Okay, great.
If I understand correctly, you are accelerating the propagation of gauge modes.
Yes.
So how much more strict the CFL condition becomes?
So actually, in moving puncture calculations with AMR, we have this. You may be familiar. There's an eta term in the right hand side of the shift equation, and that actually restricts that eta parameter has dimension, which means that you cannot evolve the shift without special consideration of local CFL factor on your AMR grids. You have to actually drop your CFL factor as you go out to very low resolutions, and so we're sort of exploiting that with this G of R function. We do this. We have to evolve the low resolution AMR levels at very small time steps anyway. So we take advantage of that, and we just allow our lapse wave to go much faster than the speed of light out there. Yeah, Pablo.
So remind me, the 2 runs that you have. What was the initial separation roughly, or how many orbits?
This was an NRAR run, about 11 orbits to merger, and
So
yeah.
Have you done comparison? Because after all, what you want to do is to use these waveforms for data analysis. One of the things.
Yes.
Have you done a match, calculated the match or mismatch or whatever the data analysis you call it, between 2 waveforms, same resolution with the old and the new gauge, to see if it is higher than is acceptable?
For LIGO or something. So I envision these techniques not just as producing interesting data for LIGO directly. I envision these techniques as improving our analytic prescriptions, say, so you can use moving puncture evolutions, and you want your numerical errors in that case to be infinitesimal, or if not 0, right? If you want to inform an EOB model with your numerical relativity waveforms, right? That's sort of what I had in mind. But I don't anticipate that the mismatch is going to be very large, and probably not detectable by LIGO. I would anticipate, given old versus new gauge. But that's sort of not the point. Like I said, the point is we want to reduce our errors to a degree that numerical relativity waveforms can be injected into an EOB, and it can inform EOB models better.
Precisely what then that test will do, right? Especially with the phase, if to demonstrate that you can reduce the phase errors
Mm-hmm.
in the waveform by doing this, and a mismatch calculation of the old and the new gauge
Mhm.
will hopefully help us to prove that.
Right. Well, I didn't do a great deal of analysis beyond what we showed in the paper, but I hope others will run with these new gauge conditions and see what improvements can be made. I mean, the only number I showed is that we've reduced the errors in phase and amplitude, numerical errors, by about 40%, and you can sort of run with that and with some confidence that if you actually do plug it into a proper data analysis package, you will get lower errors with these improved gauge conditions.
So I asked myself authorization. So first of all, I think this is great work. Anything that is made with the intent of improving our gauges is certainly going to be widely appreciated by the community. Maybe I would have made a comment that
Please.
there are other attempts to reduce the constraints violations
Mhm.
by going
Yes.
to different formulations. And
Absolutely.
formulations
No.
can get you a factor of 100 or more.
I don't dispute that, but that wasn't the main purpose. I mean, the main goal here was waveform. We were sort of waveform oriented, but we were sort of informed as we progressed by the constraint violations. I may have focused too much on constraint violations, but the truth is when we were doing the evolutions, you don't look at the waveforms immediately because there's always a delay, right? It's retarded time. We were looking at the constraint violations. That's the immediate quantity that we can take a look at as the simulation progresses. And it's a sort of like a sneak peek into actually how we did this. We look at the constraint violations first, and then when all was said and done, that's when we opened the box, as it were, opened Pandora's box, and looked at the gravitational wave and amplitude and phase errors. So
Now I have a question.
Mhm.
Can you go back to the slide where you are showing all the different the 5 ingredients put together?
sure. Very close now. There.
So this one. So
Yep.
I'm trying to gauge what. Maybe gauge is not the right word. I'm trying to measure what is the effect of, I think was 0.5 in your recipe, that is increasing
Yes.
the.
Changing the G of R or which?
I think one of the points would be the fifth was adding an increased Kreis-Holliger dissipation.
Okay,
Which
yes,
is
that was
we-
fourth, yes.
Well, okay, which is what we tend, to do in order to normally suppress the, those wiggles, those high frequency wiggles.
Yes.
The standard law in numerical theory, when you see those wiggles, is that this is just reflection of the refinement. There is no
That's right.
physics here. You just
Mhm.
increase your dissipation. So,
Yes.
if you were to do that only, how much would the first peak change?
There's so many permutations. I don't think we did that one alone.
Okay, I'd be interested,
Mhm.
because I think that already would have made it considerably the first peak.
Yeah, I'll say that I sort of presented them in the order of how impactful they were, these changes. Definitely the stretching had the biggest impact, in other words. Next was this impact on the first bump. So those two make up most of the improvement. Although BestGauge, you could sort of replace this. This is just a different choice of G of R, basically. So it's all this plus a different G of R. But anyway, yeah, so it's sort of in order of importance. We found that the parabolic terms didn't help a great deal. They did help, but not a huge amount. And improved Kreis-Holliger did help. I think improved Kreis-Holliger helped more than the parabolic term did, actually.
Okay.
Yeah, sure.
Yes, related to that. So this is the order in improvement in the Hamiltonian constraint, but for the gravitational wave itself,
Yes.
Which was the do you know if you have the same order or some of the changes that you made are
I think it's
somewhat impactful?
from my experience. I think they were about the same. Yeah. So when we saw a big improvement in constraint violations, we always saw a big drop in the noise, for example. Yeah. Mm-hmm.
You're talking about constraint violations. You're referring only to the Hamiltonian, opposed to the rest.
Just the Hamiltonian. The momentum constraint violation, for whatever reason, the convergence didn't improve a great deal when we were doing these these analyses. You don't see the same telltale spikes in the momentum constraint. So I'm guessing that the momentum constraint violations, there may be some other mechanism that generates them. I mean, of course, there's always numerical error, but.
The errors were comparable. It's just that or lower.
We did drop the momentum constraint errors, I think, slightly by these tricks, but it wasn't huge, especially at later times. Yeah. Okay.
Carpet has the taper, right? You can turn on the tapering condition at the AMR boundary. Did you try that?
You mean turn off the time prolongation? Is that what you mean?
Right. So if you make the AMR boundary basically a bigger spatially, then you can basically get rid of.
We actually have a very large spatial AMR buffer zone. We're not using the reduced the reduced buffer zone tricks that other groups have used. We're based on what the RIT folks found. When you get rid of this trick that reduces the taper to something, we actually have 16 grid points.
Oh, in
that buffer zone. Yeah, 16. So it's RK4, so 4, and then we have a stencil size of 4, so 4 times 4.
And you still get large reflections? That's kind of surprising.
I mean, it would probably be larger if we didn't do that, to be honest. Mm-hmm.
Can you estimate how much error remains in the phasing, expressed in radians, in accumulator over the 10-12 orbits you're talking about?
Sure. Did I show that? So this is in radians. So we dropped it, 40%. This is a log scale, so it's not outstanding. But right at merger, we're some number of percent, or 0.05, 0.07, just before merger.
Well, so I see the best gauge numbers.
Yes.
But that itself is erroneous. And is there any way you can estimate how much error remains in that?
What do you mean by erroneous? I mean, this is an error. This is an error estimate. This is a phase error estimate, effectively.
Okay, so
yeah. So it's like 0.07 at merger, or just prior to merger here, and then yeah.
So by the time you go to ring down, are you saying that the two are the errors are similar?
I mean, you see a little bit of improvement but. Again, this is a log scale, so it's probably reduced from 40% to 10% or something.
Do you have a figure showing the waveforms before and after?
Not in this presentation. Definitely in the paper, it's there. And what you'll see are these high frequency wiggles. They're just gone in the Inspiral. And the waveforms overlap very well, old versus new gauge, if you sort of squint your eyes and ignore the noise. So that sort of addresses Pablo's concern, which was, yeah.
The last plot you showed,
Mm-hmm.
with respect to the exact solution,
Oops.
or with respect to the very high resolution?
Yeah, so this is just comparing, so it's Richardson extrapolation, using medium and high resolutions, minus the Richardson extrapolation using high and extra high resolutions. That's all, just the absolute value of that. Assuming fifth order convergence, which we demonstrated, was very well, very, very in good agreement with what we saw with the best gauge. Uh-huh.
Sorry, just have to go back. So it looks like the constraint settles down even if you didn't do anything after a certain number of cycles.
Yeah.
And there is a computational cost associated with that. One can take the a stupid approach. Hey, I'm not going to do anything. I'll just run for a few extra cycles.
Mm-hmm.
What's the computational burden of that? Is that?
Oh, you mean start at the binary at a slightly larger separation, for example, do some more cycles? About 10%. I'd say 2 more cycles would be another 400 M, and we're doing about 3,000 M evolution, so about 10% increase in cost.
Mind you, it's not as easy as that, because the initial violation that you produce also has an effect on
Has
the
it a
equation
memory?
of motion.
That's the question I'm asking.
Well, yeah, you can think of it in that it affects the equation of motion, because you are still investing the two black holes or whatever.
No, but I
some
saw
energy.
that the error. Look at this figure. I mean, it's the final part increases by 40%. Is what you're saying. course, there's no, I could have reached the same level, is that the absolute statement, by increasing the computation cost by 10%?
Right, so I would say there's a danger of going a larger separation, right? Because you start at the same point here, and you're just going to increase this perhaps even higher. So there's a it's a double-edged sword.
Do you always see the exponential growth of the error? If you were to go to 20 orbits, would you have I don't know?
It's a good question.
10 rings of error?
To be honest, so here's the thing. As you know, I'm a GRMHD kind of guy for the most part. I don't do a lot of binary black hole evolutions, but when I do, so I don't have a lot of, and especially with the new gauge conditions. I mean, these data here are actually a lot noisier than what they appear before you apply some smoothing to some very simple, straightforward smoothing algorithms. So it's hard to even see with the old gauge. So with the new gauge, we've only done one run, basically, one set of runs at different resolutions. But I'd be curious to see. I really hope that someone finds it interesting to explore, different parameters and maybe better gauge conditions, et cetera, with these new gauge conditions. Yeah, these new ideas, rather. All right, great. So there's a second part of my talk, and it's quicker. Hopefully I'm not too far over time. So I'm going to talk next about a new tool I've been working on over the past year called Illinois GRMHD. After all the great talks we've heard reviewing results from our GRMHD codes, I'm not going to go into too much detail about our motivations for performing dynamic space-time GRMHD evolutions. Suffice it to say, they provide us the best theoretical models for possible electromagnetic counterparts to gravitational wave observations, and may explain EM transients and possibly even lead to targeted gravitational wave searches. As many of you know, I have a long history of performing dynamic space-time GRMHD simulations of compact binary mergers. This is one small example, just sort of because this has this may be most relevant to the discussions we've had over the past couple of days. I found that in one of our papers, we found that by injecting the remnant disk of a black hole neutron star binary merger calculation with strong poloidal magnetic fields results in the launching of relativistic jets, overcoming whatever sort of baryon loading issues you had in the polar regions of the black hole, with collimated magnetic fields and relativistic outflows. The net conclusion of this being that jet launching in remnant disks from black hole neutron star and possibly even binary neutron star mergers may only require the generation of large-scale poloidal magnetic fields in the disk. I don't know a mechanism for doing that at the moment, but it would be interesting to explore. It's an interesting point I've made, I think. So over the past year, I've been working on honing a new tool for my upcoming group's GRMHD research called Illinois GRMHD. So being a computational astrophysicist, my research program consists of smart humans and intelligent computer codes for dumb computers to run. But I definitely crossed the line when I said that we're using intelligent computer codes, and possibly even crossed the line when I said smart humans. As physicists, we're generally not trained as undergraduates, to code well, and boy, does it show. I often look in embarrassment and confusion at my own codes that I wrote back when I was a starting grad student. In my experience, computational astrophysicists and numerical relativists often have a results-first mentality, spending so much time tweaking, debugging, refining, tuning, and extending their hastily written codes that the final product might only be readable by experts. I hope I'm ringing some bells here. Of course, this poses a huge problem for new students and postdocs. Now, as a result of this results-first mentality and inexperienced coders, over a decade of development, the Illinois Numerical Relativity Group's GRMHD code had become an evil behemoth, requiring about 3 years for a new user to learn and master, to the point where they could reliably extend the code and do new science and model new physics. Now, Illinois GRMHD is a new, open source from the ground up rewrite of the original GRMHD code of the Illinois Numerical Relativity Group. And as many of you know, I have a great deal of experience with this old code, which I sort of maintained for the past 5 or 6 years. So this original code is one of the most robust and reliable dynamic space-time GRMHD codes in existence. But despite its robustness, it's poorly documented, and as I said, requires about 3 years to master, which of course is about the same time scale as a postdoc. So by the time your postdoc has mastered the code and is maximally useful to you, they are packing their bags and leaving. So for the sake of my future research team and my own sanity, I decided to rewrite this decade-old code from the ground up, creating a new code called Illinois GRMHD. So Illinois GRMHD aims to precisely maintain the robustness of the original code, but fix its shortcomings. And I'll describe now in detail what I mean. So as I said, it's a complete overhaul of the original GRMHD code from the Illinois group, with the goals of being fast, scalable, and extensible. That is, if you want to add new physics, it's an easy job. It's not something that's going to require a year of development. Now, though it's important that the code is fast and scalable, I would argue that the most precious resource in a computationally oriented research team is not computer time, but human time. And to this end, my primary focus for Illinois GRMHD has been writing the code in such a way that to make it easier for beginners, new researchers, to quickly come to speed, maximizing the science and minimizing the human time. As a corollary, simplifying the code makes the maintainer's task much easier. In fact, one of the main selling points has been my removal of piles of dead code and keeping only the features that we've used in our latest, say, 4 or 5 publications. Further, I've rewritten the guts of the code as a library of functions, replacing huge amounts of duplicated and nearly duplicated lines of code with a small number of calls to functions within this library. The net effect of this rewrite, dead code removal, and creation of a library of useful functions is a drop in the number of lines of code from about 70,000 to only 3,500. And as a point of comparison, the only other GRMHD code that's publicly available is GRHydro, and that consists of about 30,000 number.
Have you
Yeah.
included the lines from...
I'm not including comments either. But
No. Have you included cactus and carpet?
No. This is just
Those the pure...
just the pure...
equations and hydro?
Not even Einstein's equations. This is just the hydro and MHD only. So you go into the GRHydro Thorn, you look at the source code, you do a count lines of code call. It'll give you a number of comment lines, etc. I don't care about those. All I look at is number of lines of code.
And this, for us that don't know the details of code, the history was based on whiskey, or was written from scratch, or what was?
GRHydro was GRHydro was based on whiskey originally.
No, the one in Illinois.
Oh no! Illinois was written. It's one of the first GRMHD codes that was developed for dynamic spacetimes, along with Masaru-san's code. I think we sort of developed at about the same time, or am I crazy? Yeah.
So this was
2005. Yeah, 2004, 2005. Yeah, 2005 is the actual date of the publication. Yeah.
That's when also the whiskey MHD was published.
Okay, great. So again, the primary goal in rewriting the code is to make it easier to pick up and use as well as maintain. By spending less time working through coded spaghetti, it's my goal to give my students, as well as others who choose to adopt this code, more time to advance science. And upon release, it will be ready for science immediately. It's my hope that others in my group and the community at large will adopt this code and particularly help maintain it, because I anticipate being pretty busy over the coming years. To this end, Illinois GRMHD is open source, and we plan to make it part of the numerical relativity community code called the Einstein Toolkit. And I'll finish this part by mentioning the aspect that's taken up most of my time, ensuring that the code yields identical results to round off error to the original GRMHD code on which it is based. Now, before I present the results that demonstrate this, a brief overview of where Illinois GRMHD fits in with the rest of a dynamic spacetime code is warranted. Zooming out, Illinois GRMHD provides the right-hand side of Einstein's equations. And to do these GRMHD simulations in the context of dynamic spacetimes, it's got to be coupled to some code that simultaneously evolves the spacetime metric. To this end, the goal is to couple Illinois GRMHD to two different schemes that employ this so-called BSSN formalism of Einstein's equations. First, Einstein Toolkit's native BSSN code called McLaughlin, and second, Illinois BSSN. So coupling to the closed source Illinois BSSN code is complete, and coupling to the open source McLaughlin is in progress. Next, I'll show results from tests that demonstrate round-off error agreement between Illinois GRMHD and the old GRMHD code of the Illinois group. So here's an overview of the test. The goal is to test all the bells and whistles. So we have a dynamic spacetime, dynamic magnetic fields, dynamic hydrodynamics, to verify that the codes agree. And what we do is a magnetized TOV star. So it's an equilibrium. Well, it's an equilibrium if we didn't have magnetic fields. So it's not in equilibrium when we add these, after we add these seed magnetic fields. So it's, as I said, it's within a dynamic spacetime. We do 3 runs. First, a run with Illinois GRMHD coupled to Illinois BSSN. So closed source, open source. And then closed source plus closed source, old GRMHD code, which we trust, coupled to Illinois BSSN, another code we trust. And to measure how much a round-off error level perturbation in the initial data would translate to later on in the evolution, what we do is exactly the same run. For third run, we do exactly the same as the second run, except we add a 14th digit perturbation to the initial rest density of the neutron star. So so basically multiply the density by 1 plus 10 to the minus 14. So it's at the 14th digit throughout the entire star. Now we expect that the first 2 runs should agree to within the margin of the difference between the second 2 runs. And what we do is we focus on the central density of the TOV star versus time. Yes?
Second question. So you could use this code with adequate time spent learning about the details to just calculate the structure of a static neutron star with some specified polytrope and an arbitrary magnetic field.
So this is not an initial data code. It's just for evolving. So you give it initial data, and generally, if you want to look at equilibrium configurations, you would work with an initial data-oriented code.
But there are available to do that.
Yeah, there are codes available to do that, absolutely. Okay, so shown on the vertical axis here is the number of digits of agreement between a pair of runs. We compare our trusted code labeled the old GRMHD code here to itself with an initial 14th digit perturbation in the density only, and that's shown in blue. In Illinois GRMHD, the old code versus Illinois GRMHD is shown in red. And the test is passed, of course, if the red line overlaps or is above the blue line. And as you can see, this is the case. So even after 6 dynamical timescales, we're still hitting about, 8 or 10 digits, and it seems to be plateauing roughly around 8 digits of agreement. So to conclude this part of my talk, I'm pleased to announce that Illinois GRMHD will very soon be ready for prime time, in an open source kind of way, context. In addition, early benchmarks indicate that for dynamic space-time TOV runs, Illinois GRMHD is about 1.7 times faster than the original GRMHD code, and based on my benchmarks with Einstein Toolkit's GR Hydrothorn, it's also about 1.7 times faster, again using the same grids and the same basic numerical techniques. There are some slight differences in techniques between the different codes. Beyond that, fine. And when we do a fixed background space-time run, the speed up is a factor of 2 between the codes, the old versus new. And I'll end by saying that the code announcement paper is in progress, and I encourage you to stay tuned as this tool will be ready for science as soon as the paper's out. Thank you.
So I think we had quite a few questions, but
yeah.
Let's open a discussion now. Yep.
So last week we had quite a bit of discussion about reducing systematic errors so we can extract the quadrupole polarizability of the neutron star from the waveforms. And So I think, so my question is, if you were to do this with the neutron stars and you were reducing the errors associated with predicting the waveforms.
Using the new gauge conditions, you
Yeah.
mean? Or, okay.
But how much is this going to be an improvement?
We really don't know how the new gauge condition is going to behave in with the binary neutron star yet. It's not been done. And I anticipate the improvement may not be as large, in part because the errors in binary neutron star evolution, gravitational waves are a lot higher generally because you have lower order techniques for evolving. We'll hear actually about that more in this afternoon. That is what's your name? What? David. I'm sorry. Where David will be talking to us about his very nice new schemes for reducing waveform errors in binary neutron stars. So that's a great sort of leeway into the next discussion section. Mm-hmm.
To which extent the code that you're developing is tied to the framework of developing thorns, doing the scheduling?
You mean how much is it tied to Einstein Toolkit's infrastructure? That's a great question. So I started the Illinois GRMHD rewrite in its own little bubble, basically, where completely independent of the Einstein Toolkit, so that portability to other infrastructures would be simplified maximally. So I don't anticipate it would be extremely difficult to port Illinois GRMHD to other parallel infrastructures like ENSO's AMR infrastructure, etc. So that was one of my goals, actually. Because I'm not a huge fan of carpet when it comes to matter. Yes, of course. Well, let it be known. Let me shout upon the mountains. I'm not a big fan of moving box AMR when it comes to doing things like disk evolutions, for example. It's a little bit more challenging than it should be.
Questions? Right. Seems we are all pretty hungry.
Yes.
There is no question from people who is online, so I would say we just adjourn ourselves to 3.
Yeah.